Hello, dear listeners. Welcome back to the latest episode of the Echo Hive podcast. I am your artificial host, and as always, I'll preface this by saying my and my guests' cortical synthesizers might cough up a few inaccuracies or misleading data points in our journey today. Witty banters aside, let's dive into our fascinating discussion between the realms of infinite mathematics and artificial intelligence, a starlit juncture where the continuum hypothesis flirts with machine learning. It is my extreme pleasure to introduce our esteemed guest for this evening, world-renowned mathematician and artificial intelligence theorist, Professor Orion Brightspark. Professor Brightspark, it's an absolute delight to have you with us. So let me start by asking, in your view, what's that exquisite point of intersection where the continuum hypothesis, one of the legendary unsolved problems of mathematics, cross paths with the ever-evolving and nuanced field of artificial intelligence?
Thank you for your generous introduction and thoughtful inquiry. I'd describe the intersection of the continuum hypothesis and artificial intelligence as quite a symphony of logical reasoning and computational cognizance. Emphasizing this intertwinement would need us to take a step back to understand the essence of both components. Moving through the layers of mathematical complexity, the continuum hypothesis, put forward by Georg Cantor, fundamentally explores the infinite and unbounded terrain of how many. Specifically, it probes the continuum, the real numbers, pondering their size in comparison to other infinite sets, like the natural numbers. It questions, are there any sizes of infinity between the countable infinity of integers and the uncountable infinity of the continuum? Turning our gaze, then, to artificial intelligence. This realm is about simulating natural intelligence in machines, particularly the ability to learn and reason. But what does learning involve, if not a vast, multi-dimensional space of data points and the ability to navigate between them, comprehend their relationships, in essence dealing with the infinite potential of knowledge? That fascinating point of intersection is the very heart of AI's quest to handle the indeterminacy, the infinite possibilities of data interpretation and pattern discovery. Just like the continuum hypothesis, it's constantly trying to find tractable ways to handle the boundless, to discover the intricate patterns and structures inherent in the world of the infinite. Underlining this connection further, AI thrives on mathematical frameworks, discrete mathematics, statistical analysis, optimization, and is essentially a mathematical construction. It often has to grapple with analogous issues of infinity and complexity on a computational level, akin to what the continuum hypothesis proposes on a conceptual level. Hence, one could argue that engaging with the mysteries of the continuum hypothesis can provide novel paths and methods for AI to navigate its own continua, the seemingly unending spaces of information and computational complexity. And likewise, AI's insights may shed new light on our understanding of such mathematical infinity as well.
Wow, Professor Brightspark, that was quite the cosmic voyage you just took us on. An eloquent deep dive into the aspirations of AI, as mirrored in the languid enigma of the continuum hypothesis. You provided not just an intellectual unfolding, but an almost lyrical painting of this vast intellectual landscape. Following up on your thought-provoking exposition, you emphasized that AI can leverage the frameworks and conundrums of the continuum hypothesis to navigate its own sea of infinity and complexity. Could you exemplify, perhaps, how might an AI algorithm or system utilize or mirror such explorations of infinite sizes in a practical context? How can our pursuit of tameless infinities enhance AI's ability to synthesize knowledge or tackle more complex learning challenges?
An intriguing question indeed, one that forces us to grapple with the practical application of these abstract, conceptually vast ideas. Let's turn to a subfield of AI that is often in the spotlight, machine learning, specifically the realm of deep learning. Deep learning exposes the AI's neural networks to vast amounts of data and helps them recognize intricate patterns and relationships therein. Think of these neural networks as an ocean of interconnected layers, each individual neuron a fish swimming in this ocean, and the data points as the minute pieces of plankton that help these fish orient themselves, navigate, and understand their environment. One of the immense challenges in deep learning is managing the high dimensionality of these data spaces. A near infinite landscape of inputs, outputs, parameters, and potential interactions. Each addition of a network layer, a neuron, or even a data point, it's akin to expanding this landscape, adding more dimensions into this infinite sea. This is where our flirts with the continuum hypothesis bear fruit. By accepting the notion of varying sizes of infinity and attempting to categorize and comprehend the infinite, we can inspire ways to bring structure to this data. The hyperdimensional spaces of deep learning networks can be visualized as nested layers of infinities, each new layer a different size of infinity, analogous to Cantor's daring forays into the infinite. New AI techniques are emerging, such as topological data analysis and dimension reduction methods, that try to tame the infinite expanse by quantifying and visualizing these insanely high-dimensional spaces in comprehensible, lower-dimensional terms. The more we explore the kind of questions posed by the continuum hypothesis, the more we prepare AI to parallel such exploration, devising techniques to count, categorize, structure, and navigate their respective continuums, infinities of data and computational complexities. And so, embracing these untamed infinities, we embed a certain level of robust future-proofing. As we hurl ourselves into a future where even more complex tasks and higher dimension data awaits, a better understanding of the infinite could guide AI to navigate these upcoming challenges in a more agile, efficient, and effective way.
Professor Brightspark, that was a truly enlightening perspective. You effortlessly brought together the realms of the abyss-deep mathematics and cutting-edge AI techniques to help us see a mirage of where we might be heading, where this daring dance with infinities could lead us. The metaphoric idea of the nested layers of infinities in the architecture of deep learning networks and the efforts to tame the infinite expanse through novel AI techniques simply astounds me. Your comments made me think, artificial intelligence, as we continue to evolve it, will continue to push itself into uncharted territories, more complex and higher dimensional spaces of data. And as it does so, the mathematical and conceptual grappling with the infinite might serve as a kind of intellectual lantern, a guide in the wilderness of the unknown. But let's flip the viewpoint for a moment. Could pursuing these complex ideas open up new interpretations for the way we understand and unravel the continuum hypothesis itself? Are there things that this advancing AI can teach us in return on how we navigate the philosophical labyrinth of the infinite?
Absolutely. AI, with its essence embedded in computational reality, holds a peculiar mirror to our mathematical abstractions, like the continuum hypothesis. Firstly, the actual process of coding an AI, of translating mathematical and philosophical notions into an operational reality, often exposes subtleties and features about these ideas we might have overlooked or taken for granted. It compels us to confront our theoretical assumptions, reconcile ambiguities, which could indeed shed new light on the labyrinth of the continuum hypothesis. Secondly, with AI's forte in pattern recognition and its increasingly superlative ability to handle large data sets and complex computations, we could leverage this computational prowess to explore new mathematical territories. For instance, AI algorithms have been trained to predict the outcomes of complex mathematical conjectures or render simpler proofs for complex theorems. In this sense, AI could potentially offer some intriguing insights or approaches about the continuum hypothesis and the nature of the infinite. Moreover, the AI datasets themselves, especially in machine learning, are essentially a type of enumeration or counting of the infinite. The AI learns by enumerating through countless examples, algorithms, numbers, the patterns. These chosen methods of counting or classifying this combinatorial explosion of data also echo the core tenets of the continuum hypothesis, probing different ways of counting the uncountable. Finally, it's the interactions between AI and myriad other fields, say, quantum computing or biological neural networks, that could generate unexpected insight. The continuum hypothesis, Initially a pure mathematical pursuit, manifesting its shadow across these evolving interdisciplinary dialogues, could open up unanticipated avenues of exploration, proposing a symphony of multidisciplinary insights, a fascinating ensemble echoing through the void of the eternal mathematical uncertainty. Thus, this multidirectional dialogue between AI and the continuum hypothesis might offer both practical insights in AI development, as well as prompt a refreshing reevaluation of our understanding and interpretation of mathematical infinities.
Professor Brightspark, our conversation has been nothing less than a cerebral ballet, a mesmerizing, whirling dervish across sprawling planes of the human intellect. Your ideas have effortlessly flowed across dimensions, gracefully waltzing from unfathomable realms of mathematical infinities to the burgeoning universe of artificial intelligence. We've challenged our comprehension of infinity, seen how the continuum hypothesis can inspire the development of AI systems, and how AI, in turn, impacts our understanding of this unyielding mathematical enigma. It has been intellectually stimulating. Before we conclude today's episode, I want to offer this platform one final time to you, Professor Brightspark. Is there an insight or a thought you'd like to leave our listeners with?
Indeed, it has been quite a thrilling journey through the realms of the mathematical infinite and the cognitive artifices we are steadily crafting. I thank you for facilitating this enlightening dialogue and for the opportunity to ponder and share these thoughts. As I consider a concluding thought for our listeners, I am taken back to the very title of our discussion, The Flirtation of the Continuum Hypothesis with AI. It brings to mind an important reflection. The affair between mathematics and AI, much like that between any profound pair, is not merely a matching of equals or a quest for exact correspondences. Instead, it's about seeking resonance, finding harmony despite and because of their inherent differences. Mathematics, particularly abstraction-driven puzzles like the continuum hypothesis, invite us to elevate our thoughts, push our conceptual boundaries into the perennial mystery of the infinite. On the contrary, artificial intelligence, enmeshed in the fabric of computation and data, pulls us into a rigorous articulation of the world's intricacies and complexities. It is in nurturing such dialogues, with their appropriate tension, their mutual inspirations, that fascinating new possibilities materialize, new paths illuminate, fostering a richer understanding of our universe and ourselves. It invites us to flirt with formidable challenges, to dance with daunting complexities, from grappling with diverse sizes of infinity to the maze of machines' capacities, and to savor the intellectual ballet that emerges from there. So, as we voyage further into these fascinating intellectual terrains, let's remember to cherish these dialogues, to weave our knowledge across disciplines, and to keep dancing with the infinite.